So we're going to take a look at one more example of this method of the lucky guess, or the method of the unknown coefficients or undetermined coefficients. And we're going to do that kind of following the same rules that we set up before. Step 1 was find the homogeneous solution. Step 2 is find the particular solution, the overall particular solution, or an overall particular solution. And then step 3 was find the general solution by combining those two things. This example has kind of the added wrinkle of an initial condition. And so that means if you have an initial condition, you can go one more step and you can find the particular with the initial condition. Right? Find the particular solution with the initial condition. So that's really just the fourth step that we're going to use here. So just a reminder, we have to do the first step, finding that y sub h, and find y sub h. And I'm going to try to make this find y sub h as quick as possible because we have a really simple manipulator here. Once I rewrite this thing as my dy dt equals negative 3y, that's my homogeneous differential equation. And I know that this thing behaves just like a exponential decay equation. So it's going to have a solution that looks like this. Y equals y sub h equals constant times e to the minus 3t. And again, I'm doing this because I've done these so many times, and this is really just a review of section 1.2 using that separation of variables technique. If you don't see it right away, then that's okay. Off to the side, you can do this, do that process as well. So now we have our y sub h. The second part is use our lucky guess method to find a particular solution to the overall equation. And so in order to make sense of that, we're going to rewrite our differential equation. I'm going to follow those general steps from the previous page. You can see it's all the y terms are already on one side here. So that's kind of convenient. And now what I'm trying to do when I look at this thing is I'm trying to come up with a solution, y, that when I plug it in here and here, I take its derivative, I add 3 of itself, and I wind up with cosine of 2t. So it's probably going to be a trig function, right? You'd be silly to guess anything else. So we know we're going to guess some kind of trig. The problem is if I guess just a cosine function, and then I take its derivative, I wind up with a sine. So a sine plus 3 times a cosine, there's no way that'll work. If I guess just a sine function, then when I take its derivative, I'll get cosine, but then I will get 3 times a sine function here, and that won't work. So I know it's going to be trig, but it's going to be a little bit more complicated. In other words, it's not just a cosine function, but it's a cosine and a sine. So let me show you. The guess that I'm going to use is alpha times cosine of 2t plus beta times sine of 2t. Now, the reason that I'm going with a 2t here and here is because we have a 2t inside the right-hand side of my differential equation. And inside the argument of the sine and the cosine, that's not going to change no matter how many times I take derivatives or multiply the whole thing by something. That doesn't change. So if this right here is my guess, then I can pretty quickly say, oh, then y prime, the derivative, is just going to be the 2 would come out front. So it'd be 2 times alpha times cosine of 2t becomes sine of 2t, but there's a negative in front of it. And then when I take the derivative of sine of something, it becomes cosine. So the 2 comes out front plus 2 beta cosine of 2t, right? So the derivative of this thing is this thing, right, with respect to t. So what I'm going to do now is I'm going to take this equation, this differential equation, and I'm going to sub in my guess. I'm going to plug in my guess to see what's going on. And I'm going to have to give myself some room here. So I'm going to start by writing my derivative, which I know is this thing right here. So I'm going to write in negative 2 alpha sine of 2t plus 2 beta cosine of 2t. That plus 3 times the original guess, which is the top row over here. So alpha times cosine 2t plus beta times sine of 2t. And all of that has to be equal on the other side to just plain old cosine of 2t. Now, if you're looking at this and thinking, oh my gosh, we have alpha and beta going on. We have two unknowns, but only one equation. Not entirely. Let's expand this out and you'll see what happens here. We have minus 2 alpha sine of 2t plus 2 beta cosine 2t plus 3 alpha cosine of 2t plus 3 beta sine of 2t, and that's all equal to cosine of 2t. So what I'm going to do right now is I'm going to notice that on the right hand side I only have a cosine term. So whatever the coefficient is on this side of 1, that has to match the cosine terms on this side, their coefficients. So I basically have one equation that looks like this plus this equals this. Those three terms together give me one equation. 2 beta plus 3 alpha has to equal 1. And the reason I can do that is I just kind of drop away and I say whatever the cosine terms are, they have to have the same coefficients on both sides. So on this side, 2 beta plus 3 alpha has to be equal to 1 on this side. But what do I do with these sine terms? What do I do with this guy right here and this guy right here? There's no sine term over here. Well, there is. It's just 0 times sine, right? So the 0 has to match up with these other two. So I actually do have another equation. It looks like this. It looks like negative 2 alpha plus 3 beta has to be equal to 0 on that side. So this one equation in green actually gives me two separate equations that I can solve. Now, you can pull this off to the side and solve them, or you can hop on Maple really quick and ask Maple to do the solving for you. Either way, you're going to wind up with the following. You're going to wind up with alpha equals 3/13 and beta equals 2/13. Right? So take a second and convince yourself of where those are coming from, either using Maple or do the arithmetic and a little bit of baby algebra on your own. That's fine too. But either way, you know the alpha and the beta values that have to be true in order for this to be a solution, a particular solution. Now notice, once I plug in alpha and beta, there's no constant there. This is a particular solution. So that means I've found y sub p, and it's equal to 3/13 times cosine 2t plus 2/13 times sine of 2t. And if you were to plug this in to this differential equation right here, it would work. It is a solution. But for our purposes, we say, okay, we've got the y sub h and the y sub p. That means step 3, all I have to do is combine those to get my overall solution. And so if I combine these two turkeys, I wind up with a general solution that looks like this. My y sub h is constant times e to the minus 3t plus my particular solution right here, 3/13 cosine 2t plus 2/13 sine of 2t. This right here, that's my general solution. And normally we just say, hey, that's good enough, I'm all done. But because we have an initial condition, we were given an initial condition in the problem, it's implying we need to solve this IVP, which means we have to use that initial condition. So there's part 4 in this process. we're going to solve the IVP by using our initial condition. And if you remember from up above, y of 0 is equal to -1. And that means -1 must be when I plug in 0 for t in each spot, what I get. So c times e to the 0 plus 3/13 times cosine of 0 plus 2/13 times the sine of 0. And of course, the sine of 0 is just 0, so this whole term goes to 0. And cosine of 0 is 1, and e to the 0 is also 1. So this simplifies pretty nicely. We get -1 equals c plus 3/13. And with a little bit of effort, we subtract the 3/13 to the other side, so we have -13/13 minus another 3/13, and that means c is going to be equal to -16/13, the exact value of the constant. And that means, at the end, we get to say our particular solution, the solution for the IVP, is y of t equals our constant, -16/13 times e to the -3t plus 3/13 cosine 2t plus 2/13 sine 2t. And that, my friends, is the particular solution for this initial value problem. Now, what was interesting about this, just to recap, what was interesting about this problem, unlike the previous lucky guess problem, we looked at this and we weren't able to say it's just one thing, it's just one term. Because this is a cosine, we knew that if we took its derivative, whatever the solution is, it's going to flip-flop. So we had to include both a cosine and a sine term, right? And that's where the quote-unquote luckiness comes in to the lucky guess. That's part of the process, right? So on the next page, you'll see that it invites you to try this out and play with this on Maple. So, whoops, didn't mean to lose the screen there. What we're going to do now is hop on Maple, and in the next page, in the next video, I'm going to have you take a stab at doing this in Maple.